Hi everyone, this is Gio from Universitat Pompeu Fabra in Barcelona. See my webpage for more information about me. Today I'm back with class number 6 of the course on signals and systems. Feel free to get in touch by email if you have any doubts on this class or on the previous ones. In the last couple classes, we learned how to calculate the Fourier transform for both periodic signals and non-periodic signals. In today's class, we'll learn some basic properties of the Fourier transform, and knowing these properties will be very useful to understand the relationship between time and frequency representations of signals. Also to help reduce the complexity in evaluating the Fourier transform in many cases. Let's start with two basic properties that concern linearity and time shifting. So let's start by recalling the Fourier transform pair, meaning the formulas for calculating the Fourier transform and for inverting the Fourier transform. So a signal x of t can be obtained as 1 over 2 pi the integral of x of j omega e j omega t d omega, right? This is the Fourier representation. We can also regard this as the anti-Fourier transform, meaning that we recover x of t from its Fourier transform x of j omega. And the way to calculate x of j omega from x of t is the integral below, given by the integral between minus infinity and infinity of x of t e minus j omega t dt, right? We will find it convenient to use a shorthand notation to indicate the pair of a signal in the time domain t and its Fourier transform in the frequency domain omega, and that's indicated at the right of this slide. So we use the double-edged arrow to indicate a pair of a signal and its Fourier transform. So what's linearity about? If you have a signal x of t with Fourier transform x of j omega and another signal y of t with Fourier transform y of j omega, then the Fourier transform of the linear combination ax plus by is simply given by the linear combination ax of j omega plus by of j omega, right? So the linearity property follows readily by applying the definition of the Fourier transform to the linear combination ax of t plus by of t. And this property also holds for a linear combination of an arbitrary number of signals, not just two. Let's now move on to time shifting. So what happens in this case? Imagine you have a signal x of t with Fourier transform x of j omega, and then you apply time shift to the signal x. So you get x of t minus t0. t0 could be positive or negative, it doesn't matter. So you have a time shift. Then the Fourier transform of this time shifted signal is the same Fourier transform of the original one, but multiplied by the complex exponential e to minus j omega t0, where t0 is the shift amount. And that can also be positive or negative, right? So notice that the magnitude of x of j omega, which is a complex function of omega, is not altered, but there is a phase shift introduced, which is linear in omega. The phase shift, to be precise, is minus omega t0, so it's linear in omega. The larger t0, the larger the phase shift. Can we prove this relationship? It's actually quite easy if we want to do this exercise. So by definition, the Fourier transform of x of t minus t0 is given by the integral of x of t minus t0 e minus j omega t dt. So all we have to do here is just replacing the variable t minus t0 with a variable tau. If we do that, then we can simply rewrite the integral as the integral of x of tau e minus j omega tau plus t0, which replaces t, d tau. And the term e minus j omega t0 does not depend on tau and can be taken out of the integral, leaving this term multiplied by the integral of x of tau e minus j omega tau d tau, which is nothing but the Fourier transform of the original signal x. And therefore, we get the relationship we were looking for, the Fourier transform of the shifted signal is given by the Fourier transform of the original signal times e minus j omega t0. Let's now see an example to illustrate the properties we've just learned about, meaning linearity and time shift. So let's consider the signal depicted at the top right of this slide, that signal x of t. It has somewhat of a funny shape, and we may want to calculate the Fourier transform of this signal. We could do that by employing the formula, so the definition of Fourier transform with the integral. But in this case, I want to show you that there's perhaps an easier way of doing that. So we notice that the signal x of t can be constructed by using the two signals x1 of t and x2 of t depicted just below, right? In particular, how to do that, we will need to shift these two signals, x1 and x2, to the position 2.5 in time, right? So shift them to the right, basically delay them, and then we sum them up, but we need to reduce the value of the signal x1 of t by half, right? If we do that, we get exactly the same shape as x of t. So if I want to write what I just said in formulas, we get what this slide shows, which is that x of t is 1/2 x1 of t minus 2.5, meaning half of the signal x1 shifted at time 2.5, plus x2 of t minus 2.5, meaning the signal x2 shifted at time 2.5. Cool. Then if we just recall the Fourier transforms of these signals x1 and x2, they can be easily obtained by using the Fourier transform integral, and they are reported here for simplicity. So the Fourier transform of the first signal is 2 sine of half omega over omega, and the one of the second signal is 2 sine of 3 omega over 2 over omega, right? They are sinc functions, basically with different scaling coefficients, because they are Fourier transforms of the rectangular signal. Then we have all the information we need to calculate the Fourier transform of x of t, and that is given by compounding the linearity property and the time shifting property by e minus j 5 over 2 omega, where this factor comes from the time shift that we apply, 2.5, which is 5 over 2, which multiplies the sine of half omega plus twice the sine of 3 omega over 2 over omega, which comes directly from the superposition property. Let's now move on and see other interesting properties of the Fourier transform, namely conjugation, differentiation, and integration. Let's start with conjugation. So imagine you have a signal x of t with Fourier transform x of j omega. Then its complex conjugate signal, x conjugate of t, x can in general be complex, so doing the conjugation of x means changing the sign of its imaginary part. Well, that signal has as a Fourier transform x conjugate of minus j omega. So conjugation in time corresponds to conjugation and inversion of the variable omega, right? This has some implications if x of t is real, because if x of t is real, then by definition x and x conjugate are the same, and therefore x of j omega has to be the same as x conjugate of minus j omega, which here in this slide is rewritten in a very slightly different manner as x of minus j omega equal x conjugate of j omega. This property is called conjugate symmetry, and it holds when x is real. Can we prove the relationship that we just showed about the conjugation property? It's actually quite easy. So imagine you want to calculate x conjugate of j omega. How to do that? We can simply use the Fourier transform integral and conjugate everything, right? And that's what you see there in square brackets with a conjugate operation. Then this conjugate can be applied individually to the different terms. So x of t becomes x conjugate of t inside the integral, and e minus j omega t becomes e plus j omega t in the integral, right? And then we can just swap variables, replacing omega by minus omega. And what we obtain is that by rewriting the same thing below, x conjugate of minus j omega is going to be the integral of x conjugate of t e minus j omega t dt, which is nothing but, by definition, the Fourier transform of x conjugate of t. So we have just proven the relationship shown at the top of this slide. Let's move on to the next property, which is extremely important, and it's the property of differentiation. So this concerns the derivatives of a signal. You have a signal x of t with Fourier transform x of j omega as usual. And now what happens if I do consider the derivative of x of t? So dx of t in dt. Well, the Fourier transform of that is simply j omega x of j omega, meaning the Fourier transform of the original signal before differentiation simply multiplied by j omega. We can prove this too easily. So let's write x of t as the anti-transform of x of j omega. So simply as 1 over 2 pi, the integral of x of j omega e j omega t d omega. Now let's differentiate both sides of this equation. The left-hand side becomes dx of t in dt, and the right-hand side, by differentiating in the time domain, becomes 1 over 2 pi, the integral of x of j omega e j omega t d omega. That's because the only term function of t in the integral is e j omega t, and when we differentiate that, we obtain j omega e j omega t. So this last expression can be easily recognized as the anti-transform of a signal x of j omega times j omega. And therefore, we already got the relationship we were looking for. So the derivative of x of t in dt is the anti-transform of j omega x of j omega, which means that j omega x of j omega is the Fourier transform of the derivative of x of t in dt. So this property is actually really useful to study systems described by differential equations. And why is that? Well, imagine you have a system described by differential equations and you want to solve these differential equations. You can easily do that in the frequency domain by first calculating the Fourier transforms, and all the derivative operations translate into simple multiplications by j omega. So you obtain an algebraic equation which you can solve more easily, hopefully, and then go back to the time domain through anti-transform. We will see that in some examples. What happens when you do integration? Is something similar happening as we saw for differentiation. So is the product by j omega going to become a division by j omega? Well, something similar. So if you have a signal x with Fourier transform x of j omega, then the integral signal, the integral between minus infinity and t of x of tau d tau, has as Fourier transform x of j omega divided by j omega, as we expected, plus an additional term, which is pi x of 0 delta of omega. X of 0 is the value of x of j omega for omega equals 0, and delta of omega is a Dirac impulse centered at omega equals 0. And this impulse term reflects the average value that can result from integration. That's why we have it. Let's now see some examples, particularly of derivation and integration. Let's take as an example the Heaviside function, u of t. So our signal x of t in this example is going to be u of t, so the step function. What we already know from previous classes is that the Dirac delta of t has as a Fourier transform 1. So it has a unitary Fourier transform. So we call this signal g in this case, and it has Fourier transform g of j omega 1, right? We also know that our Heaviside function, our step function, is the integral function of the Dirac delta. So x of t in this case, which is u, is the integral between minus infinity and t of g of tau d tau, where g of tau basically is the Dirac impulse. So now we have the relationship between the Heaviside step function and the ideal impulse, right? So what is the Fourier transform of our signal x going to be? If we apply the formula, it's going to be the Fourier transform of its derivative, g of j omega, divided by j omega, plus pi g of 0, which is g of j omega evaluated for omega equals 0, times an impulse delta of omega. If we evaluate that, since g of j omega in our particular case is 1, we obtain 1 over j omega plus pi delta of omega, right? And can we go back now to the Fourier transform of the Dirac delta? Yeah, because now if we simply differentiate before we integrate, and now we're differentiating, we can recover what we already know. So now delta of t is the derivative of u of t, okay? So its Fourier transform is going to be simply j omega times the Fourier transform of the step function, which we just obtained on the line above, right? And it's 1 over j omega plus pi delta of omega. So if we simply multiply j omega by the term in the brackets, what do we get? Well, the first term is obviously 1, because the first term is given by j omega over j omega. And what about the second term? It would be j omega pi delta omega. But we remember, for the property of the Dirac impulse, that any signal multiplied by an impulse gives the same impulse scaled by the value that the signal takes where the impulse is placed. In this case, the impulse is in 0, right? And j omega evaluated for omega equals 0 is 0. So there is no second term. The result is simply 1. Well, but we expected that because the Fourier transform of the impulse is 1. So everything makes sense. Let's now give another example to understand again these properties of derivation and integration. So let's consider the signal shown at the top of this slide, which has a funny shape, and we want to calculate the Fourier transform for this signal. We could use the definition with the integral, but here I'm going to show you a somewhat easier way of doing that. So let's consider the derivative of this signal first, right? So the derivative of x of t in dt can be expressed as the simple sum of two signals represented on this slide. The first one is a rectangular signal with unitary amplitude between -1 and 1, right? That expresses the fact that the derivative between -1 and 1 of my signal x of t is constant. But then there's a couple discontinuities in t equal -1 and in t equal 1. Those discontinuities have a derivative that is a delta, and the amplitude of this delta is going to be -1 for both of them because the signal drops by a quantity -1, right? So that's how we can represent our g of t as the sum of a rectangular signal plus two negative impulses centered at t equal -1 and t equal 1 respectively. Therefore, let's calculate the Fourier transform for g of j omega. It's going to be the sum of the Fourier transform of our rectangular signal, which is a sinc. It's 2 sine of omega over omega. We've seen this before, and if you don't recall it, I encourage you to watch one of the previous classes. Plus the Fourier transform of the two impulses. How do we calculate that? Well, there are several ways. We can, for example, use the integral, or we can recall that the Fourier transform of Dirac impulse is 1, but in this case, it's scaled by a constant -1, it's negative, and it's time shifted at t equal -1 and t equal +1. And we've learned just today that a time shift corresponds to multiplication in frequency by a complex exponential. And this is what we see here. So the result is that the Fourier transform of those two impulses is minus e to j omega minus e to minus j omega, right? We can also observe that the value of g of j omega for omega equals 0 is 0. How to calculate that? We cannot directly substitute omega equals 0 because the first term, the sinc function, is of the form 0 over 0. But through a limit procedure for omega that goes to 0, we see that the first term tends to 2 because sine omega over omega tends to 1. And the remaining two terms, they tend to minus 1 and minus 1, right? So the result is going to be 2 minus 1, 0. Now we have everything to calculate finally the Fourier transform of the original signal x of t. So we know that since x of t is the integral function of g, because g is the derivative of x of t, we apply the formula that we learned today. So x of j omega is going to be g of j omega over j omega plus pi g of 0 delta omega. And how much is that? Well, it's g of j omega, which is 2 sine omega minus the two exponentials, which can be conveniently written as a cosine, as twice cosine omega, divided by j omega. The second term is 0 because g of 0 in this case is 0. Let's now keep exploring the relationship between the time and frequency domains with some interesting properties. We will consider time and frequency scaling first. So imagine that you have a signal x of t with Fourier transform x of j omega, and you scale the signal, obtaining the signal x of at. So as we saw in one of the first classes, depending on whether a is larger than 1 or smaller than 1, this corresponds to a compression of the signal or an expansion of the signal, right? The Fourier transform that we obtain from that is given by 1 over the absolute value of a times x of j omega over a. So a compression in time would correspond to an expansion in frequency, this in the case of a larger than 1, and vice versa. An expansion in time will correspond to a compression in frequency. This is a very important relationship that we will encounter again along the course. What if we want to prove this relationship? It's actually quite simple, because by definition the transform of x of at can be obtained through the integral of x of at e minus j omega t dt, and by just performing a change of variable, replacing at with tau, we obtain the integral of x of tau e minus j omega tau over a d tau divided by a or minus a depending on the sign of a. And therefore the Fourier transform of x of at is, from this relationship, the Fourier transform of x evaluated for omega over a, because you see there's a term omega over a that appears in the integration, divided by the absolute value of a. So we have seen manipulations of a signal in time that have implications on its Fourier transform. The same manipulations, if made in the frequency domain, meaning if made on the Fourier transform, have corresponding implications in the time domain. In particular, for time shifting, differentiation, and integration, similar properties hold if applied the other way around. So if we apply shifting of the Fourier transform, differentiation of the Fourier transform, or integration of the Fourier transform. In particular, the first formula shown on this slide says that if I calculate the derivative of the Fourier transform, so if I differentiate x of j omega in d omega, the anti-transform corresponding to that is minus jt x of t, where x of t would be the anti-transform of x of j omega. If I apply a frequency shift, so if I construct x of j omega minus omega 0, where in time domain this corresponds to a multiplication by a complex exponential, meaning that the anti-transform is going to be e to j omega 0 t x of t. And the value omega 0 in the exponential is the one corresponding to the shift in the frequency domain. And finally, for the integration, if I calculate the integral function of my Fourier transform x of j omega, given at the bottom right of the slide, the anti-transform is going to be minus 1 over jt x of t plus pi x of 0 delta of t. So these properties are really similar to the ones we have seen when going from the time domain to the frequency domain. The main difference is usually just a negative sign. Let's now conclude with a very important relationship, which is Parseval's relation, which says that the total energy of a signal can be computed over time or over frequency equivalently. The relation states that the absolute magnitude of the signal in time squared and integrated is the same as 1 over 2 pi, the integral of the square magnitude of its Fourier transform. How to prove that? Well, simply, if we calculate this integral of x of t square magnitude, we can rewrite it as the integral of x of t times its complex conjugate. And the complex conjugate of x of t can be written simply as the anti-transform of x of j omega, all complex conjugate, where the complex conjugate would fall on x of j omega and e j omega t, which would become e minus j omega t, as you see on this slide. Then, when going from the first to the second line, we can invert the order of integration, and we obtain 1 over 2 pi, the integral of x conjugate of j omega, times a term in square brackets, which is nothing but the Fourier transform of x of t, so it's x of j omega. Therefore, we have obtained 1 over 2 pi, the integral of x conjugate of j omega times x of j omega, which is the square magnitude of x of j omega, and the relationship is proven. Once again, Parseval's relation states that the total energy of a signal can be determined either by computing the energy per unit time and integrating over time, which is the integral of x of t square magnitude, or by computing the energy per unit frequency, omega over 2 pi, and integrating over frequency. That's all for this class. We should be now familiar with the basic properties of the Fourier transform. We'll see some more properties in the next class, where we'll focus on the relationship between convolution in time domain and multiplication in frequency domain, and vice versa. See you in the next class.